Okay, so we're continuing on in chapter 5 on probability. You are not going to be tested on chapter 5 in the midterm, but next week there is a quiz, and that will cover this chapter 5 stuff. Okay, so continuing on. So we have to consider a few quote rules, and so the first one we have is or type situations. Okay, and as far as or situations go, whenever we say the word or in statistics, or is always an inclusive or. Always an inclusive or. So that means and or. And so the if somebody asked you if we use the inclusive or and someone asked you do you have a pet or don't have a pet, your answer would be yes, right? Because it's do you have a pet and or don't have a pet, your answer would be yes. Okay, whereas because that includes everybody there. Okay, so in this case, the so when we say something like the probability of A or B, this is the probability of A happening or B happening or both. Okay, and we would say that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. If we draw a little Venn diagram, it looks sort of like this. I have a circle here. I have a circle there. We can label this A. Whoops. Let's see, I have the wrong drawing tool. Okay, so the probability of A or B is equal to this entire area here. Okay, so that's the probability of A or B. So this is equal to the probability of A plus the probability of B minus probability of A and B. And that would be, our first circle plus the second circle minus the overlap. Because if we don't subtract off the overlap, we would the total area would be too much. Okay, is that all right? So let's say we surveyed, I don't know, I'll say 240 people. And we'll say out of the 240 people, 80 people have a dog. And we'll say 70 people have a cat. I'm making up these numbers here. And we will say 30 people have both a dog and cat. Okay, and so the question is, if I pick a person at random, what is the probability they have a cat or dog? Okay, let me fire up our clicker machine here. And let me make up some answer choices for you guys. So we'll say okay, so we'll go with that. I hope this works. And let's see. Okay, so our answer should be this. Okay, let's see. We'll take a look. Indeed, most of you guys got that correct. Some of you selected the wrong answer choice. So this is asking what is the probability of having a cat or a dog. Okay, so this is going to be the probability of cat plus the probability of dog minus the probability of cat and dog. So the probability of cat, 70 out of 240, plus probability of dog, 80 out of 240, minus the probability of having both, 30 out of 240. This gives us 120 out of 240, which is a nice 0.5. So out of these 240 people, half of the people surveyed have either a cat and or a dog. Have a cat and or a dog. Okay, we'll keep the same information, and we can extend this a little bit further. And I could say, you know, what is the probability someone has a cat and no dog? Okay. You know, in the interest of time, I will not make this a clicker question. I'm just going to give you the answer here, okay? And I'll tell you how we can answer this. So we can set up ourselves a two-way table. Okay, and we can say the world can be split into two types of people, people who have cats and people who don't. Okay? And as far as dogs go, the world can also be split into two types of people, those who have dogs and those who don't have dogs. Okay? And the total number of people we've surveyed is 240. So I'm going to put 240 in this total column, or total box. And we know that 70 people have cats, 80 people have dogs in total. All right? And then we know also that 30 people have both a cat and a dog. All right, so this is these are the numbers that are given in the table. So everything else, because we have these numbers, we can figure everything else out. Okay, so 80 people have a dog, then that means 160 people do not. And if 70 people have cats, then that means 170 do not. If 30 people have cats and dogs and there's a total of 80 people, then that means this number has to be 50, because these two have to add up. These two numbers have to add up, so this number has to be 40. And thus, the number here also has to make everything add up, and so we get 120 right there. Okay. So we could set this up with counts. If we wanted to set them up using probabilities, we could have also set them up using probabilities. We would put a total of 1 in the corner, and then we would have said 80 out of 240, that's 0.333. We could have put 0.333 here. So rather than counts, we could have also used probabilities. Okay, so anyway, now that we have this table filled out, we can answer this question. What is the probability someone has a cat and no dog? That would be this box here. So our answer would be 40 out of 240 gives us 1/6 or 0.1667. Or I could also ask, what is the probability someone has neither cat nor dog? Okay, this is another way of saying probability of no cat and no dog. This would be 120 out of 240. It's this box. Okay, which is also 0.5. And that kind of makes sense, right? Earlier on the we said, what's the probability someone has a cat or a dog? And we said that turned out to be 120 out of 240, 0.5. And so if half of the people have either a cat or a dog, or both, then that means the other half of people have neither. Okay, so those two are complements of each other. Having no cat and no dog is the complement of having a cat or a dog. We can continue on here, and there's a topic we have to cover, and this is called mutually exclusive events. In mutually exclusive, if A and B are mutually exclusive, this has a mutually exclusive often means something else outside of statistics, but in statistics, if A and B are mutually exclusive, this means that the probability of A and B is equal to 0. Probability of A. This is the definition of mutually exclusive. Another way to think of it is if A happens, B is impossible, and vice versa. If B happens, A is impossible. Okay, or it is impossible for both to happen together. So the probability of A and B is equal to 0. So example of mutually exclusive events would be, A could be the coin lands heads, and B could be the coin lands tails. These two cannot happen together. Another set of events, we could say C is a randomly selected card is a heart. And D could be a randomly selected card is a spade. Okay, you cannot have a card that is both a heart and a spade. Okay, so the probability of C and D is equal to 0. So therefore, C and D are mutually exclusive. Probability of A and B equals 0. So complements are always mutually exclusive. Okay, obviously something and its complement cannot happen together. If I define E as a random card is an ace, then the probability of C and E is not equal to 0, right? Because there is a card that is both a heart and an ace. So that probability is not equal to 0. So C and E are not mutually exclusive. As far as formulas go, what this means is that we'll say if A and B are mutually exclusive, that means the probability of A or B is going to equal the probability of A plus the probability of B minus the probability of the overlap. Okay? However, the probability of the overlap, this is 0. Therefore, the probability of A or B is just the probability of A plus the probability of B if A and B are mutually exclusive. Is that okay? Hello? Okay. I feel like we're covering a lot today, but it's just the chapter on probability. It's just a whole bunch of stuff regarding events and their likelihood. It's a great chapter. All right. Okay, so we had mutually exclusive. Now we're going to talk about conditional probabilities. Okay, so we will say a conditional probability. This is the probability of some event A given, or that's another way of saying if we know some event B occurred. I'll just say it happened. Okay, and this is written probability of A given B. Okay, this is the probability of some event A if we know some event B has happened. Okay, so for example, we could say, imagine being at an airport. Okay, and we'll say, if there is a storm, the probability of a delay is 0.7. Okay, so this is the probability of a delay if a storm has happened. So we would say probability of delay given storm. And we would say this is equal to 0.7. what would equal 0.3? What is the complement of this? Yeah. It's not storm without a delay. It would feel like that could be the complement, but the complement is actually no delay given a storm. Okay? So that's different. So let me I'll change this. Okay, let me see all this. So we got probability of delay given storm is 0.7, and that means the probability of no delay given a storm is 0.3. Right? So if a storm has happened, there's a 70% chance that your flight is delayed, and there's a 30% chance that your flight is not delayed. Okay. Let me just further this, and I'll say if there is no storm, the flight can still be delayed. This time with a probability of 0.1. Right. So how would we write 0.1? What is equal to 0.1? This is the probability of what given what? So this would be the probability of a delay given no storm. Probability of a delay given no storm. So there's no relationship between this number and this number over here. Okay? There's no direct relationship there. We're just saying if there's no storm, you know, sometimes the airline doesn't have its act together and you still get delayed, or whatever other things could happen, you can get a delay. So the probability of a delay given no storm is 0.1. Okay? And therefore 0.9 would be what? Probability of no delay given no storm. Okay, so we've got a lot written out here. And so this brings up the question, well, what does it mean if I switch the other things around? Okay? Can I flip the slide here? So, you know, what does probability of okay, what does this mean? Probability of storm given delay. Okay? So this is, we would say, the probability of a storm given delay. Okay? So the idea here is that, let's say, you know, you go to the airport to pick up your friend or something. Okay? And, you know, you notice that the flight has been delayed. And let's say you don't have your phone with you, so you can't check the weather report, and now you ask, you know, what is the probability that there was a storm? Okay, that's kind of the general idea there. Does that make sense? So this is the probability of a storm if the piece of information that we know is that there was a delay. The calculations for this are a little bit involved, and I will spare them from you guys. Okay. It can be answered, but we won't bother with this. Okay, so this is so it is. We should note, okay, probability of A given B so here are a few relationships. Okay, so the probability of A plus the probability of not A given B, these two would add up to 1, okay? And then we'll say the probability of A given B and the probability of A given not B, there's no direct relationship. Okay, and then the probability of A given B is not necessarily equal to probability of B given A. There is a relationship between these two things. The relationship is called Bayes' rule, but we will not cover it in our course, okay? I should make sure my phone is silenced. Okay, so let's just kind of let's try a few examples here, and we will say, you know, we survey some people. Well, let's use our cats and dogs again. Okay, so survey 240 people about cats and dogs. Okay, let me just scroll back and get this the same chart that we had here. Okay, so I'm going to copy this. Okay, survey 240 people. We asked them, do you have a cat? Do you have a dog? And these are the responses we got. Let me just make sure, get rid of this. Okay, so let's ask a few questions. We'll say, what is the probability of someone having a cat given dog? Okay, we'll set this up. We'll use this as a clicker question. All right, and let me make up some answers here. Okay. Okay, I'm gonna hit stop here. Okay, let's see what we got. Indeed, the answer is C, and let's let's take a look. Okay, so in this case, the question is, what is the probability of cat given dog? Okay, so we're asking if, what we're basically saying is if we know, or if it is given, someone has a dog, what is the probability the person has a cat? Okay, and so what this means is that we are, as soon as we have this piece, okay, as soon as we have given dog, we are limiting ourselves just to these 80 people, okay? So the probability of blank given dog, this limits us to the 80 dog people. Okay, and so in our denominator we would put 80, and out of those 80 people who have dogs, 30 of them have cats. And so therefore, the probability of cat given dog is equal to 30 out of 80, or 0.375. And so therefore, that is our answer. Okay, some of you guys selected 0.125. 0.125 is the probability of cat and dog. Okay, and there's this difference here. Okay, cat and dog, this would be 30 divided by 240. And this question is if we pick someone at random from the table. If we pick a person at random from the table, what is the probability this person has both cat and dog? Okay. In both cases, the numerator is 30 because there are 30 people who have cats and dogs, and over here the person's going to have both cat and dog as well. So there's also going to be 30 people. The difference here is that with 0.125 cat and dog, we're saying we're going to draw someone at random from the entire table. So our denominator is 240. Over here, we're saying we know that this person has a dog. So we are limiting ourselves to just these 80 people. So cat given dog versus probability of cat and dog, they are different. Okay? Because one, we are limiting ourselves to just one subset. So when we establish some kind of equations for this stuff, we would say the probability of A given B, this is given by the probability of A and B. This goes on the numerator, and we divide by the probability of B. Okay? If you have tables, if you have a table with counts, you can also do the count of A and B, and I think this is what most of us did on the last example, divided by the count of B. This is going to be okay. Contrast to the probability of A and B, which is going to be the count of A and B divided by the total count of the table. And if you look at, the difference between the probability of cat given dog, you'll see that it's this, and that is different from the probability of cat and dog. Okay, as far as these equations and formulas go. The labels of A and B are arbitrary, so we can also have probability of B given A. This is equal to the probability of B and A divided by the probability of A. Now, we should note that the probability of B and A is equal to the probability of A and B. And so therefore the numerator portion of all of this is going to be exactly the same. It's just that the denominator changes. So the given part always goes in the denominator. All right. So as we're talking about conditional probabilities, we have one more type of, I guess, two types of events or something, okay? We can say events A and B can also be independent. Okay, don't get independent mixed up with mutually exclusive. Independent means the outcome of one event has no influence / or is not associated with a change of the outcome of the other event. So it means that if A happens, it has no effect, it has nothing to do with whether B happens, okay? Okay, and vice versa. If B happens, it has nothing to do with A happening. That's what it means to say A and B are independent. So, for example, two separate coin flips, those are independent of each other. The outcome of one coin flip has absolutely nothing to do with the outcome of the other coin flip. Those are independent events. I'll say separate coin flips are independent events. Maybe I should say the outcomes of separate coin flips are independent events. Okay, so with that in mind, what would the probability of A given B be equal to? So if A and B are independent, then the probability of A given B, this will equal the probability of A. Exactly, okay? So whether B has happened or not, the probability of A happening, given that B has happened, is just the probability of A. All right? And this is how we can check to see if two events are independent. Are two events independent? We check to see if probability of A given B is equal to the probability of A. Okay? Yes.
Is this the same as being mutually exclusive?
It is not. It is not the same as being mutually exclusive. I'll explain that. So this is how we can check to see if A and B are independent. Okay, so if probability of A given B equals the probability of A, they are independent. I guess we'll have to save the example for next week on Monday, but this brings up a good point, though. Conceptually, I'll give you one more question, and this will be maybe we'll see. Okay, so if two events A and B are A and B are independent, A and B are independent, could they be mutually exclusive? Yeah, so this will be a yes or no question. So A will be yes, they could be, and B will be no, they cannot be. Yes, could be mutually exclusive. No, they cannot be. Okay, so you can, if A and B are independent, could they be mutually exclusive? Yes, go ahead and talk to we're going to run out of time. Okay, so I'm going to hit stop at the 1 minute mark, so get your clicks in. Okay, get your clicks in. Click, click, click. Okay. The answer, it's pretty divided. The answer is B, and let me explain. Okay. So if A and B are mutually exclusive, hang on, you guys. If A and B are mutually exclusive, that means if A happens, B is impossible. Right? Mutually exclusive means if A happens, B is impossible. And vice versa. If B happens, A is impossible. Okay? If A and B are independent, then if A happens, it does not influence B. Okay? And so being mutually exclusive makes the other thing impossible, which is the opposite of saying it has no influence. Okay? Therefore, if they are independent, they cannot be mutually exclusive, and vice versa. Okay? So if A and B are independent, they cannot be mutually exclusive. Okay. We'll end there. Good luck as you guys study. We'll see you guys on Friday for the midterm.